I lied previously. Water, or H2O, it actually exists as H plus or hydrogen cations and OH negative anions. It's almost as if Mickey Mouse here did like a Van Gogh move and chopped its ear off. The ear, or the hydrogen, leaves with its proton, but not with its electron. Remember, hydrogen's electron is attracted to anything else but its corresponding proton. The OH part leaves with all of the electrons from the water molecule, making it an anion because it has one extra electron. H plus cations will be incredibly significant for us in this class because these are what the pH scale measures. pH is not a measurement of acidity. It's more of a measurement of the ratio of H plus cations to OH negative anions. When they're in proportion of twice as many hydrogen as OH anions, then we have water. The problem is that your body makes H plus cations all day long. No, it does not make the corresponding OH negative anions, just those H plus cations. And this tips that balance or proportion of H plus to OH negative, making the cations outweigh the anions. And since pH is a measurement of that proportion, the number pH changes as well. This picture here is the pH scale. And I want to point out that this is a man-made scale. I mean, we needed some way to quantify pH, and so somebody came up with an equation, and this scale is it. The pH scale ranges from 0 to 14. And it doesn't matter, I have some pH scale pictures where 0's at the bottom of the picture, 14's at the top. I even have one where the pH scale is horizontal. It doesn't matter. It ranges from 0 to 14. And the numbers, they all indicate something about the proportion of H plus cations to OH negative anions. In the pictures on the right, you can see those proportions of the H plus cations that are in red and the OH negative anions that are in purple. Let's start at the midpoint of the pH scale, which is a pH of 7, or is a pH that is neutral. This means that the number of H plus cations equals the numbers of OH negative anions. No, it does not mean that there are 7 cations and 7 anions. In fact, the 7 is the result of a logarithmic equation that I beg you we not concern ourselves with here in this class. So basically, water has a neutral pH, and blood is just a little bit higher than that, with a pH that comes in at 7.35 to 7.45. All right, let's first consider acidic substances. These are substances that have a value of 0 to 7 on the pH scale. These are substances that have an excess of OH cations an excess of H plus cations compared to the OH negative anions. And these are things such as orange juice, the love of my life, coffee, not my husband, and other non-consumables such as battery acid, which actually has a pH that is very close to the pH that is in your stomach. Oh, and heartburn is the over-acidity of your stomach contents, as well as the burping up of those contents, but that's for another lecture. I once had a student ask me what was the pH of the most acidic thing on Earth, and I said 0. I proclaimed it, actually. But then he asked what would happen if we discovered something that was more acidic than that. And I said that we'd probably rearrange the logarithmic scale or the logarithmic equation so that the new substance was pH was 0. And he replied that that was cheating. Yes, but that's also science. We have to adjust our technology and our measurements for new discoveries. So if acidity means that you have excess H plus cations and you are making excess H plus cations all day long without making the corresponding OH negative anions, then your blood becomes acidic throughout the course of the day. Your negative feedback mechanisms are reversing that change to keep your blood within the correct pH range. Complicating this is also the fact that carbon dioxide is acidic, and you make that all day long too. Your life is basically a big battle to keep from being acidic. But don't worry, it's not just humans that do this. It's pretty much all living things. We are not unique in that sense. So we have a feel for acidity. It's the values on the pH scale, the proportion of the H plus cations to the OH negative anions, and the fact that you are drawn to that part of the pH scale daily. The values of 7 to 14 on the pH scale reflect alkalinity, which we can also call basic, not acidic. You can use either term in this class. If you take a chem class, you might have a professor that forces you to use one or the other. So these values of 7 to 14 on the pH scale indicate that there are less hydrogen cations than the OH negative anions. And this scale, or this part of the scale, reflects things like Tums, Rolaids. What other medications can you think of for heartburn? Oh, blue cheese, which is neutral because you pair it with those hot, spicy, and acidic wings. Powerful cleaners such as bleach and ammonia also fall on this range of the scale. We don't deal with alkalinity in the human body nearly as much as we deal with acidity. Hydrogen cations or protons, they're constantly being produced by just living normal metabolic processes. You are always making hydrogen cations, which means that you are always going acidic throughout your day. Your life is a battle to be less acidic. You create hydrogen cations through the breakdown of proteins, from anaerobic respiration, from metabolizing lipids, and from the loading and transport of gases like oxygen. It's all about these hydrogen cations, and managing them will manage pH. During aerobic respiration, like if you do intense exercise, glucose gets broken down into lactic acid, but the lactic acid dissociates right when it hits blood. In starvation, or if you just go too long between meals, untreated diabetes, or low carb diets, the body starts breaking down fats for energy. And the liver converts the fatty acids into ketone bodies, which release hydrogen cations when they dissociate in blood. When the body breaks down amino acids, nucleic acids, phospholipids, phosphoric acid, it's all produced. Phosphoric acid is produced, and it quickly dissociates into hydrogen cations and phosphate groups. So there are tons of sources of hydrogen cations every day, making your ECF pH go more and more acidic. There are three mechanisms that counteract this tendency toward acidity. Right now, buffers in your blood are your compensatory mechanism, most likely. If they get exhausted, then your body will turn to a respiratory mechanism to try and help mediate pH. If that doesn't work, then your body's going to turn to the kidney to try to help pH. And it's going to have to convince it to do it. They're used in this order. And if your kidney actually is getting involved in managing your pH, it means that you're on thin ice. It doesn't get involved in pH management unless the other two systems have been completely exhausted. Thankfully, there are substances in your blood that are called buffers. And buffers resist a change in pH, and they do this by absorbing excess cations or secreting. Well, not secreting, but giving off. If your blood is acidic, which it usually is, there are substances that can bond with the excess hydrogen cations and raise your blood's pH back into normal. These are buffers that are not only helping to resist change, but they also help to bring it back into the correct range. The bicarbonate anion is one that is very important. This is HCO3 with a little negative, and it's made up of the carbon dioxide that your cells make in cellular respiration. You might also know about sodium bicarbonate, which is baking soda. Bicarbonate is a blood buffer, and you have a limitless supply of it because you make carbon dioxide all day long. This is great because since you're making all of those acidic hydrogen cations all day long, the alkaline bicarb can bond with them, removing their effect on your pH. There's also a protein buffer system that's concerned with the loading and unloading of oxygen from hemoglobin. I don't know if you remember this, but in internal respiration, hemoglobin dropped off oxygens, but at the same time, it also released hydrogen cations in the process. And many of those hydrogen cations are buffered by the proteins that are in blood. So what happens if all of the buffers in your blood are occupied and you're still acidic? Your lungs and your kidneys start to play a larger part in managing your pH. But they don't like to do that unless all of your blood buffers are exhausted. Remember, I said that carbon dioxide is acidic? Well, if your blood is too acidic, your breathing rate will increase, trying to blow off the carbon dioxide that you're making and raise your pH. If your blood is too basic, your respiratory rate will decrease, or you might want to breathe into a bag, as your body tries to hold in that acidic carbon dioxide and lower your pH. If your lungs aren't able to affect the desired change, then the kidney will reluctantly kick in and manage those hydrogen cations for you. No matter what, whether it's the lungs or the kidney, these buffering systems bring the blood right back into its pH range, just into it, and then they stop. They don't return your blood to like the middle of its pH range. They just do what's effective and then they stop working. Variable reabsorption and secretion of hydrogen and bicarbonate ions contribute to pH. Thus far, you've seen two examples of acid-base regulation throughout the renal tubule and the collecting system. The cells of the PCT secrete hydrogen ions in exchange for bicarbonate ions. And then those intercalated cells of the distal tubule and collecting duct, those were cells that actively secrete hydrogen ions, but only under the influence of aldosterone. There is another mechanism in the renal tubule. There are cells that are stimulated when the pH of the blood becomes abnormal. If the pH of the blood decreases, making it too acidic, there are enzymes in the distal convoluted tubule and collecting duct that will remove an amino group from the amino acid glutamine that's present in cytosol. By doing this, these cells of the tubule, they generate two ammonia molecules, which we don't want, and two bicarbonate ions, which we always want. The ammonia gets secreted, right? Like that just stays in the tubule, bye-bye. But the bicarbonate ions are reabsorbed. And so in the filtrate, the ammonia molecules bind and buffer hydrogen ions to form the ammonium ion. Both ammonia buffering and the bicarbonate ion reabsorption, both of those things help to raise the pH of blood back to normal, which is the more common situation, right? Because we go acidic every day. If the pH of blood increases and blood becomes too alkaline, it's not exactly the opposite that happens. The tubule cells start to just limit their reabsorption of bicarbonate ions from the filtrate, and they end up secreting them in urine, lowering the pH of blood.